So, why do ceramic objects wear out over time? When we place a restoration in a patient's mouth, for example, rarely does it break on the first day that it's placed. However, most of them will wear out within the patient's lifetime after some long period of time. Could be months, hopefully will be years. And usually the patient is applying the same forces, mechanical stresses to the restoration or tooth on the first day as they do later on. So these forces are not great enough to cause failure on day one, but for some reason they're great enough to cause failure months or years down the road. And so why is that? It's because, usually not because the forces are getting stronger, the strength of the material is decreasing over time. And the strength of the material is decreasing because the flaws that are present in that material are growing over time. We call that subcritical crack growth. It's crack growth that occurs up to the point where we reach the critical stress intensity factor. The crack gets large enough for those three factors multiplied together, the Y factor, the applied stress, and the square root of the crack size. When the crack gets large enough, those equal the fracture toughness of the material, and then the material fractures all of a sudden. And we have had experiments to demonstrate the subcritical crack growth occurring over time in dental ceramics. The first one was conducted by Dr. Anna Savas and his assistant Ben Lee, and they used a micro-hardness indenter, a diamond pressed into the surface of dental porcelain to induce cracks in it. And then they watched those cracks every hour, and then every day, and then up to 2 weeks later, and noticed that the cracks slowly grew over time under a applied stress. And they also noticed that the cracks grew faster when they were in water than when the material was in oil. So a wet environment, such as the environment in the oral cavity, leads to faster subcritical crack growth and shorter lifetimes for ceramic materials. And another experiment was conducted at Medical College of Georgia by Dr. Carl Fairhurst. He took ceramic bars, dental porcelain bars, and had a testing machine slowly bend them until they fracture. So he applied stress that was increasing slowly over time and measured the average strength at which the dental porcelain failed. And you see that as he measured it, there was a distribution among the porcelain specimens. They didn't all have the same strength because they started with different sizes for the largest flaw in each one. And however, he didn't use a constant rate of stressing. He had some groups of specimens he tested very rapidly, and some he took a long time to test, up to 1 day. And what he found was that when he took up to a whole day to test the specimens, that the average strength of the specimen was lower than when he tested them quite rapidly. And the strength got lower and lower the longer period of time that the specimen was under this increasing levels of stress. And so the cracks were growing over time during the test. That's what caused the change in the average strength. So we have two mechanisms by which subcritical crack growth occurs in ceramics. The primary mechanism is called stress corrosion. Stress corrosion was first modeled in the doctoral research of Dr. Steve Freeman, who also incidentally is from my alma mater, University of Florida. And I have a cartoon here to depict for you how that works. We have the silicon and oxygen ions that we find in a ceramic material. The red line here is meant to represent the surface, looking under a very powerful microscope, the surface of a ceramic material. And this ceramic material might be in a wet environment. And so we have a notch or crack on the surface, and it has a H2O, a water molecule, penetrating that. And if we bend the ceramic material, that induces in the surface this stress or force that tries to open the crack, and that increases the stress intensity factor at the tip of the crack to the point where it can break the bonds between the silicon and the oxygen ions and cause the crack to grow, causing A in our equation to become larger, and also sometimes increasing Y factor that describes the sharpness of the flaw. What can happen with the water in the environment is that can penetrate to the crack tip, and because water is a polar molecule, the slight positive charge on the hydrogen ion will be attracted to the negative charge in the oxygen anion in the ceramic and will form a bond with it, and the slight negative charge in the oxygen anion of the water will be attracted to the positive silicon cation and form a bond with it. And this acts as a catalyst and reduces the stress intensity factor that's required to break apart the silicon and the oxygen. And this process not only occurs over time, but it accelerates over time. And I'll demonstrate that here for you with a graph of the logarithm of the crack growth velocity on the y-axis and the stress intensity factor on the x-axis, which again is the sharpness of the crack times the stress times the size of the flaw that's present. And at the same time, I'm showing here the surface of a piece of dental porcelain that was fractured in my laboratory. This fracture surface has on it a set of arrows showing a halo-like appearance around this original flaw marked with a red oval on the surface, and that flaw grew slowly over time, more and more rapidly, until it reached the critical stress intensity factor, and then it suddenly accelerated and grew rapidly through the material. And that point at which the crack growth accelerates from micrometers per day to meters per second is what causes that halo appearance to be formed on the fracture surface. That's what we call the critical flaw when it reaches that point. So what we see by this graph is that up to a certain stress intensity factor, KTH, the threshold stress intensity factor, up to that point, no subcritical crack growth will occur. The cracks will remain small forever, and the material would never break. After we pass that point, which is unfortunately a very low stress intensity factor for most ceramics, so we tend to always be passing that point, then we start to get some crack growth occurring. And as the crack grows larger, A increases, and when A increases, that causes stress intensity factor to increase. And when the stress intensity factor increases, the graph shows that the velocity of crack growth increases. And so this is a vicious cycle, which causes the crack to not only grow, but its growth causes it to grow faster in future time. And this continues to occur until the crack is growing fast enough that the moisture can no longer diffuse to the tip of the crack, and that causes the rate of crack growth to level off at this point where there's a short plateau. And then we reach the critical stress intensity factor, the fracture toughness, at which moisture is no longer necessary to catalyze crack growth, and crack takes off very rapidly and within a fraction of a second breaks through the rest of the ceramic component. We mentioned that there are 3 methods of improving the fracture resistance, and the first one was reducing the severity of flaws to increase the strength and lifetime of the material. But what do we mean when we say reduce the severity? How can we do that? There are several methods of flaw reduction. One is to avoid machining or cutting the ceramic into the shape that you want, because this could lead to a surface that's very rough or has lots of cracks in the surface. For example, in this dental framework, you can see under transillumination subsurface crack that has been induced in the material by the machine that milled it into the shape it has. And another way is to remove any cracks that might be on the surface by polishing the material. And polishing, of course, is kind of like machining. It introduces new cracks. But if we use very fine abrasive media, the new cracks that are induced are very small ones. And so we are essentially replacing the large cracks on the surface with a set of smaller cracks, increasing the strength of the material. And then another way to do that is to avoid making the flaws in the surface to begin with, and we can do that by, instead of machining the ceramic to get it into the shape we want, we can melt the ceramic and squirt it into a mold, and similar to how we would process a polymer or a metal, but then we are limited to a very narrow selection of ceramics that are available to us. As we mentioned, most ceramics have very high melting points, so these would be the ceramic materials with the lowest melting points that are available. Okay, in addition to the strategy of reducing the severity of flaws present, another strategy was placing a residual compressive stress on the surface of the material to squeeze the flaws that are present close and try to prevent them from growing or to reduce the rate at which they grow. And this is a process known as tempering. It should not be confused with the tempering process of heating up a metal after it's been quenched. The ceramics researchers copied the name that the metals researchers were using, but the procedure and the effects that are occurring in the microstructure have nothing to do with each other. So tempering in ceramics is entirely different than tempering in metals. And what we do is we place a stress. I have a negative here to show that it's a compressive stress, and that is squeezing this crack on the surface closed. And that's going to be all over the surface of the material. And just like a magnet, when you have a north pole, you have to have a south pole in a magnet. When you place a compressive stress on the surface of a ceramic, the interior develops a tensile stress. So you actually increase the stress in the center of the ceramic material. It turns out that this is usually not a problem, and here is why. When we bend the ceramic material, for example, if a patient bites down on a fixed partial denture, then one side of the material will develop a large stress on it, the side that we bend away from. And the interior of the material develops very little, almost no stress, due to the mechanical bending. And the other surface of the ceramic material actually develops a compressive stress in it squeezing the cracks closed. So what happens is we add the mechanically induced stress to the residual stress that was already existing in the ceramic before it was mechanically loaded, and the sum of those determines the behavior of the crack and whether or not it will grow. So the mechanical stress that's induced has to come up to and exceed the residual stress. In this case, it's not. 20 is not exceeding the 30. And so the material will behave as if it's below the stress intensity threshold to cause subcritical crack growth. And that crack will never grow in this case. On the opposite surface, we have negative 30 and negative 20. And those together equal negative 50. So we have a large compressive stress on that surface, squeezing cracks closed. This is not a problem because ceramics break in tension, not in compression. So a compressive or squeezing stress will not cause failure on the other surface. It would have to get to 3 to 5 times the stress on the tensile surface of the object to cause failure, and that rarely happens. And this shows the effect on a Weibull chart that tempering has. Just to remind you, here's what the Weibull chart for non-tempered materials looks like. After we do the transformation to the axes, this strange log-log transformation, we expect to see a straight line. But after we temper a ceramic material, we no longer have a straight line. We have this curved behavior. And that will be curved because there's a threshold stress below which the material feels as if there is no stress mechanically being placed on it, and the cracks don't grow at all. And so we have a point at which the probability of failure suddenly drops off to 0% probability of failure at all stresses and loads below that point. So this has the effect of making the lifetime of the ceramic component less variable. So not only does it make the component stronger, but it makes it more predictable at the same time. And it also makes it less susceptible to future damage, as long as that damage does not penetrate the exterior compressive layer and make its way into the interior region that had the tensile stress in it.